Professor, for inviting me. Let me give my talk with the title, Eigenvalue Estimates of the Basic Dirac Operator. Let's start with my talk by giving the background of Dirac operator shortly. So, what is the first of the differential operator D satisfy this equation? This question was raised by P.A.M. Dirac, 1928, and studying the special relativity. So, you can see this photo. I got this photo, the Solvay Conference from Curie Museum in 2005. So here is him Dirac, maybe in here 27 age, very young scientist. And this is Einstein, and this is Lorentz. Yeah, so this Solvay Conference is a very, very famous conference in physics and chemistry. So this is the fifth Solvay Conference in 1927. The topic in this conference was the quantum physics. So almost all scientists won the Nobel Prize. Yeah. So first, this photo was taken by my poster with the smartphone, and then I found this clear photo from the website. Very nice. And so this Solvay Conference was started in 1911 and was held every 3 years. And 1913. At this time is the First World War areas. Yeah. So. Yeah. And so, for example, the plane. What is the this operator satisfying square is reflection, and then we define D. If I like this one, here is gamma x, gamma y is 2 by 2 matrix. Then gamma x square, gamma y square is minus identity, and this is skew symmetry. And then this square is Laplacian. On R3, if we put gamma 1, gamma 2, gamma 3, then if we define D like this, then D square is equal to Laplacian. So generally on Rn, there exists D such that D square is Laplacian if and only if there is lambda I such that this relation. Here, sigma n is this space. This space is called Spinor space. Yeah. So we define the Clifford algebra. Let V be a real n-dimensional vector space with inner product. The Clifford algebra is the associated algebra with the multiplication is this. for example, Clifford algebra is a finite dimensional vector space of dimension 2n. For example, n is equal to 0, CLV is a real line, and CLR is complex number space, CLR2 is quaternions, and the CLR3 is like this. And we define the spin group by the multiplication, even element, and with length 1. So, for example, spin R is minus 1 and 1, spin R2 is unit circle, and spin R3 is like this. So, the spin group is a Lie group. So, spin group is a non-trivial double covering of S of V. Moreover, spin V is compact connected for n is greater than 2, and simply connected for n is greater than 3. Let Mg be an oriented Riemann manifold. Then the structure group of Tm is SON. So we can give the question: can we rip the principal frame bundle to a vector bundle Tm with the structure group spin n? Because spin is the double covering of special orthogonal. And generally the answer is no. So we can define the spin structure on M. Spin structure is a principal bundle P spin M over M with fiber spin N. And Riemann manifold is the fixed spin structure is called the spin manifold. For example, yes, there are many there are many manifolds which admit the spin structures like this one. And now M has spin structures. Then we can construct the spinor bundle, some vector bundle like this one. This is called spinor bundle. And each section is called spinor field. Okay. So now we can define the covariant derivative on the spinor bundle by the relation between the spinor group and the special orthogonal group. So, locally, the spinorial connection is given by this. Here is a spin representation. Another one's Clifford multiplication. Yeah. And then we can define the curvature tensor, and it is given by this equation. Here, R is usual Riemann curvature tensor. And we have two important equations. So this is a Ricci curvature. This sigma is a scalar curvature of manifold. So now Dirac operator D is defined by D psi is this one. So of course this is independent of the choice of local orthonormal basis, and if M is compact and D is formally self-adjoint, which means this one. So there are many results about the Dirac operators on ordinary manifold. So I am interested in foliated case by spin structure. So I will give some definition of foliation. Roughly speaking, the foliation is decomposition of the same dimensional submanifold, connected submanifold. So the connected submanifold is called the leaves. Okay. Yeah. This is a manifold, and we have a local chart. This one is like this affine subspace, and we call the coordinate as distinguished coordinate or foliated coordinate. So from the condition 3, condition 3 means the submanifold L alpha is isomorphic to p-dimensional affine subspace in Rn. Okay. Then we have the coordinate change like this type. Here is the x is coordinate of leaf, and y is coordinate orthogonal part, transversal part. And then this is the intersection on intersection part here, and this map is leaf preserving. Okay, so this is leaf preserving. Yeah, I catch some throws. This is the sun rising, the model of sun rising. And sometimes this is leaf, especially this is singular foliation. And this is torus, solid torus. Yeah. This draw was captured from you know the Chuboy in Tokyo University. Yes. And his website, in his homepage. So now we define the spin structure on the foliated Riemannian manifold.
What's the leaf here?
This one?
Yeah.
This one, I'm sorry?
What's the leaf for this curve?
You can, if you consider just the torus and we can consider T2 or T solid torus, no problems. And when you consider torus, we can consider the quadratic curve, and then you identify this one and this one. And solid torus, you consider the surface. So no problem. So let MGMF, F is the foliation, and oriented Riemannian foliation of codimension Q and bundle-like metric. Bundle-like metric means the metric which which the distance between the leaves are constant. So, okay. And L is the tangent bundle, and Q is the normal bundle. And usually the study of this tangent bundle is called tangential geometry, and usually in this part is transversal geometry. My research is focused in transversal geometry. So then we have exact sequence like this one. So roughly speaking, the quotient bundle is at each point is considered as tangent space of quotient manifold. Exactly not. So foliation is a transverse spin foliation if the normal bundle admits the transverse spin structure P spin Q. And similarly, we define the foliated spinor bundle. And then the transversal Dirac operator DTR is defined by this type. So the different point of usual case is this term. Here the kappa is the mean curvature vector of the leaf. And transversal Dirac operator was introduced by Professor Campbell in Illinois University. Now he retired in 1988. So we have Lichnerowicz-type formula about the transversal Dirac operator. On transverse spin foliation with the delta core closed, then we have this equation. At the first, Campbell assumed just usually kappa B is closed, is proved, but delta kappa B is not. So for simplicity, he considered this condition. Afterward, that was afterward some geometry proved there exists a bundle-like matrix satisfying this equation. Here, this is a second application type of this, and the kappa sigma is this is scalar curvature of quotient manifold, and kappa B is mean curvature. Usually, the ordinary manifold can be considered as a foliated manifold with point foliation. Then, this equation is the ordinary Lichnerowicz formula. Okay. So here, operator this is non-negative and formally self-adjoint. Now we define the smooth foliated section satisfying this one. Then dB also restricted to this space. Then dB is called a basic Dirac operator. This operator has discrete spectrum. So 2001, I estimated some eigenvalue estimation. Yeah, in general case, an ordinary case, this inequality was proved by by Thomas Friedrich in 1981, and then there are many eigenvalue estimation about the first eigenvalue of the basic the Dirac operator. And 2001, I developed that inequality to the polated case. Yeah, here, yes, F has satisfying this equation, then the eigenvalue lambda of the basic Dirac operator satisfies this inequality. Here is the dimension of co-dimension of foliation. Yes. And this is proved by defining this modified connection, and we calculate the length of this derivative. So, if f is minimal, then the basic Dirac operator is just differential operator and co-differential. And so, delta B basic Laplacian is equal to dV square. So P is basic harmonic form. Also, this is a differential, co-differential is defined on the basic form. So I did not show here. Then we have this equation. This means this one is eigenvalue of dV. So, but lambda 1 is smallest. So this is impossible. So in other words, P psi 1 is equal to 0. That means in the limiting case, means the foliation satisfying the equality. Then HB1 first cohomology, basic cohomology group is vanish. From this one, if we have basic harmonic one form, a foliation has basic harmonic one form, then eigenvalue is more sharper than before. So I proved this one. If M admits a non-trivial basic harmonic one form of constant length, then eigenvalue, first eigenvalue satisfies this inequality. This is sharper than before. Now we also change the conformally, the transversally conformal change of the bond-like metric. Then we have these equations. Also, we define the foliated spinor bundle associated with G bar conformal metric. And we have these relations. And from such a conformal change, we have another estimation like this one. So if the transversal scalar curvature is non-negative, then the first eigenvalue satisfies this inequality. Here, mu1 is the first smallest eigenvalue of this operator. We call this operator as a basic Yamabe operator. This is general, more extended case. And also, recently, I have improved report previous inequality like this one. Yeah. Now, I estimated to the calculation. Calculation means the normal bundle has a Kara structure. So, for example, the Hop vibration is a very nice example, and also the Sasakian manifold, also the example of Kara foliation. And exactly, F is said to be Kara foliation. Means first, we have almost complex structure J satisfying this equation, and also J is parallel. And omega is a basic two form. It's the basic Kara form. And then foliated spinor bundle is decomposed is this form by the action of basic Kara form. Here, SR is the eigenspace corresponding to the eigenvalue, this one. So, this eigenspace is decomposed like this one. And then here, this space has element of this type, satisfying this equation. Then we can we prove the this inequality on the Kara foliation. This is also the sharper than the inequality in Riemannian foliation. Especially in the limiting case, the F is minimal and the transversal Einstein and all the complex codimension. In other words, there are sharper estimation when F is even codimension. So this was another geometry proved. So even case, this inequality hold. And recently I proved. We defined the type R because the eigenspace is decomposed like this type. So the eigenvalue lambda of this type is called type R. And then we have this equality, this equation, and this equation we can calculate. So, transversal F is Kara foliation, then transversal scalar curvature is non-negative, then eigenvalue lambda of type R of basic Dirac operator that satisfies this inequality here. If R is m plus 1 over 2, then this is the first inequality on the Kara foliation when the codimension is odd, and R is even. In other words, R is equal to n over 2. Then this means another this is inequality. So this is general inequality. So this talk is the summary of my works until now. Yes. Thank you very much.